Welcome to Spring LIB.
We are given this overall reaction that takes place within a galvanic cell at a temperature of 25 degrees Celsius. We are told what the value is for the equilibrium constant K. We want to determine from this information what the value is of the cell potential at the concentrations given in the problem statement. And we also want to determine what the value is for the change in Gibbs free energy at these conditions. So based on the fact that this is the overall reaction, we know that these are the two half reactions that were combined together in order to produce this overall reaction. We can see that we need to multiply the second reaction by 2 to cancel out 2 electrons on each side. And so the equation that we use to find the cell potential at non-standard conditions is the Nernst equation shown here. And so those 2 electrons correspond to that variable n. And so the only other variable that we need to know to plug in is that reaction quotient Q. However, for the first part of this problem where we are finding the value of the cell potential at standard conditions, we know that we have a value of the equilibrium constant K. And we also know that at equilibrium, the cell potential E from the Nernst equation will be 0. So we can use that information along with the value of K to first solve for that cell potential at standard conditions. So again, at equilibrium, the cell potential is 0. We are solving for the cell potential at standard conditions minus 0.0591. We just saw that N is equal to 2 moles of electrons. And since we are at equilibrium, the Q is now K. And so if we plug in that value of K that we are given, which is 2.79 times 10 to the power of 7, then we can rearrange this equation to solve for that cell potential at standard conditions. And when we do that, we should get a value of about 0.220 volts. And now we need to use this value to plug it into the Nernst equation again, and this time solve for the reaction quotient Q based on the concentrations that we are given to again calculate the cell potential. So this is the expression for Q that we have based on the overall reaction, where we do not include cobalt as a solid. And the concentration for Cr3 plus that we are given is 2 molar, and we square that for the numerator. Concentration of Cr2 plus that we are given is 0.3 molar, and we square that. The concentration of CO2 plus is given to be 0.2 molar. Calculate out that ratio for Q, and it comes out to 222.2. And so the Nernst equation to solve for that cell potential at non-standard conditions. We know that the cell potential at standard conditions we just found to be 0.220 volts using the equilibrium constant. We subtract 0.0591 over 2 times the log of that value of Q that we just found. And when we plug that all into the Nernst equation, we find that the value for the cell potential at these concentration conditions is about 0.151 volts. And now we need to solve for the change in Gibbs free energy at these conditions. So this is delta G not at standard conditions. So it's negative NF E, where E is the value we just calculated, so not the standard condition value of the cell potential. So this is equal to, again, 2 moles of electrons for N. F is Faraday's constant, which is 96,485 coulombs per mole of electrons, and E is 0.151 volts or joules per coulomb. When we calculate that out, we get delta G in units of joules, and if we divide by 1,000, then delta G at these conditions comes out to about negative 29.1 kilojoules.